Hello, this is Neil Singer with part two today of our CJP Safety Education Foundation safety podcast on landing performance. Today, we are going to be talking about the use of runway analysis in helping us determine landing performance and solve some problems, some A-B type of choices when we're faced with multiple options on landing and trying to decide what the best path is. Many of you have probably heard me speak before on runway analysis, usually in conjunction with takeoff performance planning, but it can be a really powerful tool for landing performance as well. So let's take a look at how we can use it in the case of a specific accident that happened to a light jet several years ago. So using runway analysis for landing, we're going to look at the particular case of one landing overrun. But first, let's just review real quickly what runway analysis is and why it can be useful to us. It is a single point performance solution for both takeoff and landing that solves for all of our potential performance limits, runway limits, climb limits, and obstacle limits. It's able to maximize takeoff weight through a series of complex calculations to create an optimal path. Also able to do similar calculations as we're going to look at today for landing. It's really an established best practice for higher turbine operators and large Part 91 turbine operators. And it is even becoming required in some nations through the SAFA check, which is a enhanced inspection of the aircraft pilot and planning that has gone into a particular flight, a lengthy ramp inspection, essentially. How do we get runway analysis? At the present time, there's only one retail commercial vendor of runway analysis for general aviation, which is called the Aircraft Performance Group. They make an app. They actually have a newer version of their app, but the older one is still supported, called Preflight. They also have an online portal, apg.aero. They provide the runway analysis through third-party flight planning vendors. So Air Inc., Universal, Honeywell, some of the big names in flight planning software, as well as flightplan.com. All of these are utilizing the same engine and the same software made by the Aircraft Performance Group. How much? Numbers I've heard anywhere from $50 to $150 per month per tail, depends on exactly how you sign up, what your primary portal is. The iPreflight app tends to be at the higher end of that range, $100 to $150 a month per aircraft number. So let's look at a particular incident. This was a Phenom 100 that ran off the end of runway 21 in Sedona, Arizona, approaching 10 years ago. There were a lot of things that contributed to this accident. And what I think is interesting about this, though, is how we can look at a couple of the variables. And even though they may not have actually directly contributed to the accident, they are instructive. You know, we can use them and use the analysis of them to inform our own performance planning. But first, let's just do a brief overview of the actual flight. The VREF for the weight that was present at time of landing would have been calculated to be approximately 99 knots. The aircraft ended up flying a fairly unstabilized approach. At 500 feet on final, their indicated airspeed was 124. That's REF plus 25. Our current CJP SOPs call for any exceedance of VREF by more than 20 knots inside 1,000 feet in IMC or 500 feet in VMC to require an immediate go-around. So certainly by 500 feet, being REF plus 25 would have been called for a go-around. They were on a 3.7 degree approach to the runway. Nominal is 3 degrees. This particular runway may have had a slightly lower or higher PAPI. That can happen at times, but again, 3.7 degrees is certainly higher than a normal approach path to a runway. Descending at 1,400 feet per minute, our SOPs call for no greater than 1,000 foot per minute descent inside a 5-mile final, inside the final approach fix, or the approach is deemed unstabilized and should result in a go-around. And the thrust levers were at idle. Stabilized approach calls for thrust at a normal setting. Having the thrust levers at idle would certainly be indication that the approach was unstabilized as well. So a lot of warnings here at 500 feet. The energy state of the aircraft was clearly too high. As the aircraft approached 150 feet above field elevation, they received a TAWS warning of sink rate, pull up. This particular aircraft has a TAWS B system, and to get a pull-up warning at 150 feet AGL, that would have required approximately a 1,500 foot permanent descent rate. So that excessive vertical speed continued even to just outside the runway threshold. They did touch down within the first 1,500 feet of the runway despite the excessive energy, but they touched down at just a little bit over 18 knots over ref with a slight tailwind a slight increase due to the altitude. They actually had a slight headwind, which we'll talk about in a second. The ground speed was 123 knots. So they're moving over 200 feet per second at the moment of touchdown with only about 3,500 feet of runway remaining in front of them. As we saw, the aircraft ended up going off the end of the runway, down a slope, thankfully came to rest without any fatalities on board. So I said we'd talk about the wind. So they did land on runway 21, and the winds at the time of the accident were reported as 250 at 5, gusting 14. So the choice to land on runway 21 would, at first blush, be understandable. But when we look further at the situation at this airport, we see that runway 21 has a pretty significant downslope, 1.8%. All of the citations we fly have a runway slope limit of plus or minus 2%. So this runway is approaching the limits of what we are allowed to land on in terms of a significant slope. So we're faced with a choice here. Would we want to land on a very steep downslope runway, but with the benefit of the headwind? Or would we prefer to land uphill, have the hill assisting us in stopping the aircraft, but then be landing with a tailwind and have a higher ground speed at touchdown? The key point here is that this is not a decision we should ever try to make intuitively. There's just too many variables. We are allowed to land on slopes anywhere from 0 to 2% pitch. We could land with up to a 10-knot tailwind, and we don't really have any certifying limit of how much headwind we could land into. We all have our SOPs that might limit what the absolute winds we'd be comfortable landing in are. But the point is, there's quite a range of slope and wind conditions that we might be facing. And to try to intuitively decide at which point the tailwind uphill is safer than the headwind downhill is just not likely. So using Runway Analysis, in this case, the iPreflight app, we can run both cases, landing 2-1 and landing runway 3. We're going to be looking at the right side of the screen here. This are screenshots from an iPad. So landing in Sedona, we've put in 2-1. We've put in winds 250 at 10, sort of splitting the steady state and gust conditions that existed at the time of the accident. Temperature 25, altimeter 2992, not going to have a great effect on this particular situation. And the first thing I want to point out is that in our options, we have the option to have a unfactored landing distance. We've previously talked about safety margins for landing and how our CJP SOPs recommend either a 60 or 80% landing factoring safety margin. Fortunately, built into iPreflight is the ability to select either that 60 or 80% landing factor. So we've said if we have a pilot with time and type, with recency, and with visual or electronic slope indicators available, that an 80% landing factor might be appropriate in those circumstances. So we can select the 80% landing factor in our options, and then we can look at what is our actual landing distance and what is our landing distance using that 80% safety factor. And recalling that another way to say 80% safety factor is that we would want 1.25 the AFM landing distance to actually exist. So we see that landing on runway 21 with a approximately 10 knot headwind component, just under 10 knots with the geometry, we would need a test pilot to have 3,357 feet, everything perfect. And with our safety factor, we would say we would want just under 4,200 feet of runway to stop this airplane. We can run the same case for runway 3, and we can see that the situation is significantly better. We would expect a test pilot to stop the airplane in just a little over 3,000 feet, so 300 feet less in the absolute best case situation. Or with a little bit of a safety factor, we could see that we would be expected to stop the airplane in just over 3,800 feet. Now, in both cases, even with the safety factor, the runway required was less than the runway present. Again, this particular incident was a direct result of a very unstabilized high energy approach. But we can put aside that for a second and we can learn a smaller but really important lesson here, which is we often would not want to be doing what might be intuitive in terms of looking at the wind, looking at the runway conditions. The presence of a large slope might go unnoticed if we don't utilize software that is going to give us a very detailed indication of which is the safer of choices.